So if there is a force on moving charges in a, what's capital B an abbrev for? So if you want to, you can make a little note, a reminder to yourself, that's going to be my abbreviation for magnetic field. If there is a force on moving charges in a magnetic field, and I showed you last day that there is, I showed you the little jumping wire that moved around. We watched some videos of other experiments. We know how to find the direction of the force. There's 3 right-hand rules. How do we find the magnitude? The first equation I'm just going to give you, the magnetic force, I'll call that FB for magnetic force, on a moving charge is Q lowercase v uppercase b, QVB. The Q can be uppercase or lowercase. If it's a really big charge, we use a capital letter Q. If it's a small charge, we use a lowercase q. V is speed, not voltage. That's why I said lowercase b. And B, lowercase v, and B is magnetic field. We have to add one more thing, though. Look up. Actually, the velocity and the magnetic field have to be perpendicular to each other. If they're not at right angles to each other, no force. Where Q equals the charge in coulombs, V equals the speed in meters per second, and B equals magnetic field in Teslas. What if they aren't perpendicular? Well, if they aren't perpendicular, if the velocity is cutting through the magnetic field at an angle, did I say angle, everybody? It's a component, okay? So here's a picture of a charge Q cutting through a magnetic field at an angle, and it ends up, when you do the trig, being sine. And so actually the correct equation for magnetic force is technically Q V B sine theta. That's not the one that I put on your formula sheet. By the way, I should have said, can you all look at your formula sheet and find where this charge is, and that'll tell you the area that we are now in. If they're parallel, if the velocity and the magnetic field are parallel, what would the angle theta between them be exactly as a number? If they're parallel, what would the angle theta between them be exactly as a number? 0. What's the sign of 0 on your calculator? Is it 0? Yeah, no force. If they're at right angles, what would the angle be exactly as a number? Would the sine of 90 be 1? Because if the sine of 90 was 1, then the sine theta would vanish, and I would have QVB like I just told you with the perpendicular set. Yes? Okay. So particles experience no force if they move parallel to the magnetic field. They experience maximum force if they move at right angles to the magnetic field. And so if they're moving perpendicular, it's QVB. The maximum force is experienced when particles move in a direction that is perpendicular to the magnetic field. So example 1, I like example 1, I like example 1. A proton, it's a proton, so we're going to have to use some of the numbers from a proton from our formula sheet. Moving at 1.7 times 10 to the 6th meters per second, enters a magnetic field at right angles to the field. So this is the maximum. I'm going to call this A. I'll call the second question B. So, okay. David, what does A want me to find? What's causing the force? The magnetic field. So the force is going to be QVB. Yeah. Nope. That would be a really weak speed. It would hardly be moving at all. This is the velocity. Good question, though. Okay, you okay with that? I just reparroted the equation that we learned today. Q, it's a proton. Tell me the charge on a proton. It's on your formula sheet. It's not 1.67 because if you look at the units next to that, that's kilograms, which is not charge, that's mass. I'm going to say, Niels, that's a silly mistake. We don't want to do it again. What's the charge on a proton? I'll give you a hint. It's a pretty elementary concept to figure out. The elementary charge. V, 1.7 times 10 to the 6th. B, 0.15 Teslas. What do you get? Get your calculators out and start crunching the numbers, please. It won't make a difference right now, but remind me to fix it later if you want. If you press the show me your calculator. If you press the mode button, or it might be setup. I can't remember which. And I get a force of 4.08 times 10 to negative 14 newtons. Now you might say that's a small force. No, it's not. Because remember, a proton has a small mass. Niels, what does B want me to find? What did I find in part A? The net force. You know what? I'm going to use acceleration equals F over M, right? F equals what? And the force is 4.08 times 10 to the negative 14 divided by, Niels, what's the mass of a proton? That's the number that has the kilograms next to it. Yes. Times 10 to the negative what? Thank you. Yeah, negative. And so even though this seems like, oh, you know what, Mr. Duke, use your answer button. Even though this seems like a small force, if I divide it by the mass of a proton, this proton is accelerating at 2.44 times 10 to the 13 meters per second squared. .44 times 10. Mr. Dueck, I got a problem with that because that's faster than the speed of light. First of all, that's an acceleration, not a velocity. Yeah, but Mr. Dueck, that means after 1 second, if it started at rest, it would be going 2.44 times 10 to the 13. Actually, the acceleration is not making it speed up or slow down. It's making it change direction. We'll talk about that in a second. Are those numbers correct? You get the same thing as me? Okay, I forgot to do a check. Okay. That's on a single charge. Now let's ask, what if we stick a bunch of charges in a wire? What's the magnetic force on a wire? One charge QVB. Turns out we can use that to extrapolate what it would be for a bunch of charges holding hands in a wire. So if we have a wire carrying a current perpendicular to an external magnetic field, it will also experience a force. That was, I showed you a video of the jumping wire when we turned the switch off and on, and I even brought up my own apparatus. I had a swinging wire where we saw it swing out or swing in, depending on whether we turned the current on or off. The direction can be found using the right-hand rule. This is going to be the hi-fi hitchhiker. The magnitude depends on three things: how strong the external magnetic field is, stronger field, stronger force; how strong the current is, because a bigger current means more charges per second, and each charge will feel a force; and how long of wire is in the magnetic field. If you got more wire in the magnetic field, that's more charges, more force. We're going to start with a single charge. We said this: FB equals QVB. Current is Q over T. That means that I can replace Q with current times time. Q is it, I think, is the joke that I made last unit. So I'm going to do that on this line here. I'm going to go I T times VB. And then, if you would be so kind as to circle the t and the v. That's time times speed, or Brendan, speed times time. Brendan, do you know what speed times time can be replaced with? Distance. I can write this as current times distance times b. But by the distance, what we really mean is the length of the wire. So I'm going to cross out the letter D, and I'm going to replace it with L for length. That's the force on a wire. It's ILB. Although, to make it easier to remember, we usually write it as the force on a wire is Bill. B-I-L or L. Did I put a capital L or a lowercase L on your formula sheet? I can't remember. Lowercase. So if I did a lowercase L, I always, whenever I do a lowercase L, I always make it a cursive so you can tell that's not a 1. Oh, look up. Peter, you too. Callie, you too. Look up. Keep up here. Same restriction as before. All three of these have to be at right angles. Well, of course they do, because that's how my right-hand rule worked. It was all this 90-degree right-hand rule thing. Oh, B equals magnetic field in Teslas. I equals current in amps. That also means that V over R could go in there as well, because V equals I times all of our circuitry stuff still applies. And L is length. That's the word length written terribly. Length of wire. And here's the important thing we're going to underline. Inside the B field. It's not the total length of wire, it's how much of the wire is inside the magnetic field. Oh, and that's in meters. So example 4 says, find the magnetic force and the direction on the wire. Just glancing at this is already something that creeps me out. What creeps me out? So the first thing I would probably do is go, nice try, 0.7 meters. The rest of the units are good. Let's find the magnitude, then we'll do the direction. So this is the force on a wire. The force, magnetic force on a wire is Bill. How strong is the magnetic field in Teslas, Noor? How strong is the magnetic field in Teslas? Look at the question. You're way overcomplicating it. How strong is the magnet in Teslas, Noor? Thank you. How strong is the current in amps? How long is the wire? 0.7. What do you get? 21? Units. It's a force, Noor. It's a force. Units. Yeah. Okay. Now, I'm picking on you because I know you're having trouble. Don't feel bad. It wants the direction. So let's see. What direction is the current? Look at the picture. What direction is the current? Everybody's going to point your right thumbs to the right. Now, right now, I can hold my hand all sorts of orientation. What direction is the magnetic field? So I have to hold my right thumb pointing to the right, fingers pointing down the page. For me, it's easier to go like that. What direction is my palm pointing? Which way will this wire feel a force? Into the page. You can write that in one of two ways. You can write or That's into the page. This equation has four variables, Lean, F, B, I, and L. As far as I'm concerned, if I give you any three, you can find the fourth. You can get whatever by itself. If the force on a 5 centimeter, nice try, Dueck, 0.05 meter, piece of wire carrying 12 amps is 1 times 10 to negative 3 newtons, what's the magnetic field strength of a perpendicular field through which the current passes? So they've given me the magnetic force on a wire, and I know that that's going to be BIL. Lean, what's example 5 asking me to find? What is the what? Which of these variables is our abbrev for magnetic field strength? I'll give you a hint. It's the second letter of the alphabet. How would I get the B by itself? How would I move the I and the L over? What are the I and the L doing to the B? Adding, subtracting, multiplying? Our formula manipulation is fair game again. I agree with you. So the magnetic field strength is going to be the force divided by IL. It's going to be 1 times 10 to the negative 3 divided by 12 amps, 0.05. What do you get? Sorry? Can you give it to me in scientific notation, please? I don't know. Let's see. Typo. Where's my typo? Oh. You got that there? 0.001 and then 6 repeats? Yes, I'll go 1.67 times 10 to the negative 3 units for magnetic field strength. This is our new unit, Teslas. Is that very big? Stronger than Earth's magnetic field? A really big magnetic field is 1 Tesla. Like I said, Earth's magnetic field, it's on the order of 10 to the negative 5 Teslas. And I think now we're turning the page. So here's one cool application. Years ago, in about 1995, a movie came out called The Hunt for Red October, based on a book by Tom Clancy. And the premise of the book is the USSR, this was before the USSR had collapsed, has a secret submarine that you can't detect underwater because it has no moving parts in its engines. It uses something called a magneto-hydrodynamic drive. And here is the physics behind it. Here is the side view of the mini sub. We have a North Pole magnet right here. This is the outside of the sub. We have a South Pole magnet right here. Let's draw in the magnetic field lines. Which way do magnetic field lines point from? What to what? No. And you need to memorize that. So let's draw in 3, 1, 2, 3 magnetic field lines. Okay? What I can't show you in the diagram, in real life, what we also have is a metal plate on the outside that we're looking through right now. And we charge that metal plate up positively, and then the current flows through the seawater. So these X's are designed to show that the current is just flowing into the body of the submarine. So what direction is the current flowing? Into the page. Point your right thumbs into the page. This is the hi-fi hitchhiker. What direction is the magnetic field? So into the page. What direction magnetic field? Down the page. What direction will the charged particles feel a force? Out the back like a jet engine. What are the charged particles? Seawater. You have a underwater jet engine, no moving parts. I don't know if this has ever been built. It was a big thing in the 80s as a kind of neat idea, but this would be very difficult to detect underwater. So force pushes water out the back. It's a neat application. The bigger issue, the bigger change would be this massive chunk of metal moving through the Earth's magnetic field because they would interact with each other. And I believe that is one way they try and detect submarines. Now, if you're far enough down, that change could be so negligible that we don't have the instrumentation to detect it. So I've been talking about magnetic fields. I talked about a solenoid last day. A solenoid is a wondrous device because it allows us to customize how big a magnetic field we want. We can control it easily. What do we need to know for a solenoid? First of all, you need to know capital N. That's going to be the number of turns of wire around the solenoid. L is how long the solenoid is. I is how strong a current you're running through the wires. And B is the magnetic field that you get. Ampere determined that the magnetic field inside a solenoid depended on certain variables. He found that more current, stronger field, so I is going to be on the top. He found that more turns of wire, stronger field, so N is going to be on the top of the equation. He found that a shorter solenoid, the more you compress the wires, the stronger the magnetic field. L is going to be on the bottom. So he found magnetic field was proportional to N times I divided by L. But in the same way that we needed to put a constant big G right here to get an answer in newtons per coulomb, a kilogram, in the same way we needed to put a letter K, 9 times 10 to the ninth, right here to get an answer in newtons per kilogram, we're going to need a constant right here to get an answer in Teslas. And I'm going to introduce you to perhaps the coolest named constant of all time. So we get this. The magnetic field from a solenoid is equal to mu with a subscripted 0, N times I over L. Mu with that 0 is pronounced mu naught from the Brits, so a 0 is a naught, N-A-U-G-H-T. And it's 4 pi times 10 to the negative 7. The units would be Teslas, meters per amp. And it's called, oh, what a great name, the permeability of free space. Mu naught is the permeability of free space. Yeah. If I get the mu naught by itself, amps would go to the bottom, length would go to the top. It's on your formula sheet. Can you find it? It should be right underneath the K 9 times 10 to the ninth, I think, or right around there. Should be on the same chart that has big G and little k and the mass of an electron and the... It's there, yes? First of all, Mr. Dueck, why is pi showing up? The universe likes that number. Okay. This one here, many of you, the first time you try typing this in, you're going to get an error on your calculator. We'll have to do a cheap workaround. So patience when we do our first question. But let's make a list where N was the number of turns of wire. I was the current running through the wire. L was the length of the solenoid. Oh, and B is the magnetic field in Teslas. What this means is if I want to have twice as strong a magnetic field, I got 3 options. I can wrap twice as many turns, make N twice as big. I can double the current, or I can just make it half as long. It really lets me pinpoint customize a magnetic field to any size that I want. There is another version of this. When you actually buy a solenoid from an electronics store, they don't tell you N, they don't tell you L. They actually give you N divided by L as a ratio, and they call it lowercase n. And this would be in turns per meter. So a second version of this for a solenoid is mu naught lowercase n times I. How will I know to use that one? Oh, they didn't tell me the total number of turns of wire, and they didn't tell me the length, but they did tell me how many turns per meter. We'll use both in just a second. And can you all look and see where both of those are on your formula sheet so you know? Okay. That's all of the equations for this mini unit right there. We're done. Next class, we're going to look at some cool applications. But today, we're going to try some of this. Example 7. A solenoid is carrying a current of 4.2 amps. If the solenoid is 1.2 centimeters, nice try, Dueck. 0.012 meters long, and is made up of 750 turns of wire, what's the magnetic field at its center? Okay. Noah, what's this question asking me to find? Now, a few minutes ago, Lean found the magnetic field, but that was using the F equals Bill. They gave me a force and a current. Looking at this, we're talking about a solenoid, so my first thought would be to use the solenoid magnetic field equation, which is mu naught N times I over L. What are we trying to find? Okay. By the way, I would also have no problem giving you the magnetic field and asking you to tell me how many turns of wire do we need, or how big a current do we need, or how long does this solenoid need to be. But this is going to be straight plug and chug. It's going to be 4 pi times 10 to the negative 7. What's N, Noah? Yep, don't overcomplicate it. You have to memorize what's what, but it's not, rocket science this time. What's I? Bonus, you've already learned that from the last unit. Over, what's L? Yeah, so it's as long as you kind of know what each of these letters means, we picked good letters, you should be able to figure this out. All of you, every one of you wants to try this because a bunch of you are going to get an error when you hit equals. So everybody wants to try typing this in. In fact, I think it's the Casios that are going to give you the error. Yeah, it is. But first of all, I want to make sure they all get the error and who gets the error. Who got an error? What brand of calculator, David, do you have? Casio? Casio? Yeah, I think the TIs can handle it. What you're going to have to do, here's the problem. The Casios, they forgot to write that pi can be put in front of scientific notation. You will have to type, instead of 4 pi times 10 to negative 7, you'll have to type pi times 4 times 10 to the negative 7. That's going to be your workaround on the Casios. And then you're fine. Pardon me? Okay, then if you still got an error, I'll come look in a second. But what you would type would be this, if you didn't want the error on the Casios. You would go, is there more than one thing on the top? Bracket around the top. And then you would have to type pi button times 4 scientific notation, negative 7 times 750 times 4.2 close bracket divided by 0.012. You should get 0.329, really 0.33 Teslas. Fairly strong magnetic field. If you figured it out? Okay. Anybody else still getting an error and not knowing why? Okay. And on the TIs, you can just type it in as is. And it's just whoever coded that, programmed that, forgot to write a couple of lines of code to say, oh yeah, you can also have a symbol in front of scientific notation. Yeah. Oh yeah, it also has mu naught programmed in. Yep. I'm just going to go 0.33 Teslas. Okay. Example 8. This was my attempt at a 3D drawing, which I'm terrible at in Word. We're looking down the solenoid like a telescope. In other words, don't draw this in, but the solenoid kind of extends into the page. I just couldn't get that to work very well. So we're looking down the solenoid. It says find the field, magnitude, and direction at the center of the coil. Well, first let's find the magnitude. It's, ooh, hang on before I start going any further. Okay. Ava, what's this 10? What's N? It's a trick question. There isn't. What's L? It's a trick question. They didn't give me a length. What did they give me instead? They told me the number of coils per meter. They gave me little n. And so I'm going to use the second version, which is mu naught little n times I. And that's what's used the most in the electronics industry. Turns per meter. You don't buy a solenoid based on how long and how many turns it's going to. How many turns per meter do you need? Give me that solenoid, please. So it's going to be 4 pi times 10 to the negative 7. The permeability of free space. Matt, what did you learn in school today? Mummy, I learned about the permeability of free space. It's 4 pi times 10 to the negative 7. Oh, Matt, you are ever so clever. Oh, that was clearly a little fantasy, right? Because, yeah, clever. Ava, what'd you get for a magnitude? 0.032? Direction. So now we have to use our solenoid rule. What do you think these arrows are meant to indicate? Of something. Current. And I guess because this is extending into the page, we'll have to hold the solenoid in our hand. And if you want to, you can hold your paper up to match my screen, or you can leave it flat on your desk. But if I hold the solenoid in my hand and it's going into the page, I'm either holding it like that or like that. Oh, wait a minute. I want to curl my fingers in the direction of the current. What direction is the magnetic field at the center of the solenoid? Okay. Now you could write out of the page, or I could do that. I'll change colors so it just stands out a bit more. I'll do it in red. So F equals QVB on a single charge. Put all the charges in a wire, and we reasoned our way to it must be Bill. Oh, and I can figure out how strong a magnetic field. I can calculate the magnetic field from a solenoid by mu naught n times I over L, or if they give me turns per meter. So you're an electronics company. A company approaches you and they say, we got 30 centimeters of room in the device that we're building, and we need a magnetic field of 6.28 times 10 to the negative 3 Teslas. We have a 5 amp current source. Then in my factory, how many turns of wire am I going to have to put around the solenoid? Oh, okay. I'm going to write the solenoid equation. B equals mu naught n times I over L. Ryan, what do they want me to find here? Get the n by itself, please. Good. Mu naught and the I. Yeah. And what I'm trying to get you to realize is if you are an electronics company, you can really customize to meet whatever your customers want. That's the beauty. One of the reasons solenoids are so ubiquitous and used all over the place. It's I can create a magnetic field to whatever I need. It's going to be B 6.28 times 10 to the negative 3. L, oh, thank you. I should have crossed out the centimeters and made it 0.3 meters. Nice try, Dueck. All over 4 pi times 10 to the negative 7 and 5 amps. I tried to make this work out nearly evenly because technically turns of wire should be whole numbers. You shouldn't have 3,219.4 turns of wire. We try and do so. What do you get? All of you again want to try typing this into your calculator. If you're not, you're setting yourself up for some ugliness on the test. Sorry? 300 units, turns of wire. What's your homework? So you can try number one. Number two, notice it's floating in midair between balanced gravity and magnetic forces. In other words, your first step is going to be gravity equals magnetic force. mg equals Bill. Skip 3. 4, you want to do a free body diagram. It's asking you to find tension. The forces are going to be gravity down, tension up, and then FB either up or down. You'll have to figure it out from your right-hand rule. And who's winning? It's a tie. Get the T by itself because it's not accelerating. See if you can figure that out. That's a nice advanced question. 5 is pretty plug and chug. 6 is pretty plug and chug. 7 is good. 8 is good. 10 is good. 11 is good. 12 is good. You can skip 13, 14, 15. 16 is good. Put your pencils down, look up.